So I have here a parabola in standard form. This type of equation is also referred to as a quadratic. And we're going to go through trying to solve this. And we have to use a technique called completing the square in order to convert it to vertex form in order to solve this particular expression. So the reason for that is that this type of equation it's not linear. You can't use linear algebra on it. So for example, something like this, sine of x squared cubed plus 4. That doesn't look like a line at all. But if you make a little replacement, right, replace this stuff, sine x squared cubed. If you replace this with just a symbol, you end up with this instead. Well, that's just a line, right? mx plus b. If you can do this, make a replacement to turn something that is really complicated into an object with a single multiplication factor or division factor, and then a plus or minus factor, then you are able to use linear algebra to solve this. Right? You just put in a number, put in your 0, subtract 4, divide by 3, cube root, arc sine, square root. There's only one operation to do at a time. If you look at this, there's no replacement I can make to have this look like this form. If I replace the x's with a smiley face, I still end up with 3 smiley face squared plus 30 smiley face. Anytime you have a thing and that same thing squared, you're looking at a non-linear relationship. You cannot use linear algebra to solve a non-linear equation. It means you have to use one of your non-linear techniques, either the quadratic formula, which we're about to develop, or factoring and case building. So I'm going to do completing the square factoring on this particular expression, and we're going to get an answer. And then I'm going to look at where all the numbers track through so that we can maybe build a formula that uses this number, and this number to save you the heartburn of having to try and do completing the square factoring over and over and over again every time you come across this type of nonlinear equation. So first off, I need to bend this thing into vertex form. I'm just going to quick write one down here. Vertex form looks like this. Number in front, and then a number in there, and a number at back. Now this, I just made these up. It has nothing to do with this. But instead of having an x squared and an x, I have the x squared and the x contained in this perfect square bracket. So I'm going to have to build a perfect square bracket for this particular thing. So if you look, there's that a value, right? This number up front. It's up front here, and it is not blended in with the x. So I'm going to have to peel this off of both pieces that have an x. Okay. Now, if I were to expand this thing here, x minus 3 times x minus 3, I'd have an x times an x squared, a negative 3x, and a negative 3x, which is a negative 6x, and a negative 3 times a negative 3, which is a plus 9. And do you notice that this number is twice that? And do you notice that this number is that number squared? So I have to build this out of that. well, if this number here and this number are related by doubling it, then this has to come from x plus 5 squared. Half of 10 is 5. So I'm just going to do this here. X times x would be x squared. 5x and 5x would be 10x. I have that much. 5 times 5 is 25. So this piece here, that's missing. So I'm going to introduce it. Now you're allowed to do that to an equation as long as everything you do on the left side, you do on the right side. So I introduced 25 times 3 on the left side. So I'm going to have to introduce 25 times 3 on the right side. So this equation is still balanced. I can rewrite this as x plus 5 squared. And I don't need this anymore. Get that out of the way. Now I have something that is linear. I can replace x plus 5 squared with a smiley face in this particular expression, and I would end up with 3 smiley face minus 15 equals 75. That's linear. I was able to replace the complicated thing with a single symbol that is multiplied and has something subtracted from it. So using this completing the square technique, I was able to convert this nonlinear expression into a linear one that I can now solve. So I'm going to keep working on this. I'm going to kick the 15 over here. So instead of subtracting, I'm adding on that side. I'm going to divide both sides by 3. Going to square root. And anytime you use the square root to break a square, you have to consider both the plus and the minus options. And finally, I have to subtract 5. So if you were to get out a calculator and actually execute these operations, you would end up with the answer for x, the place that will give you 0 here. Now, I'm not going to do that right now, because the point of me showing you this is to try and look at these numbers here, see where they ended up and where they came from out of your original equation, to try and build something so that we don't have to do this over and over again. And I do want to stress at this point that completing the square is not the task we're after here. It's how to use this thing called the quadratic formula. So if this seemed a little sorcerous to you, that's okay. It is a factoring technique that should be in your toolbox, but I'm not going to ask you to do it on this particular topic. So there's my answer. I'm going to erase all this interim work because we don't actually need that now that we have an answer. I'm going to put this up here so I have some room to work. Plus 15 over 3. All right. Now I want to look at this original equation, and I want to try and find these numbers in that equation. So do you see that this number here is there and there after we do all this work? So whatever whatever this number is, it ended up there, and it ended up there. I'm just going to use a capital A to represent that letter here as we go through and work. So that 15 at the back, that one's easy to find too. Right, this 15 is that 15. But notice the sign has switched, so I'm subtracting that number. So subtract negative 15 would be plus 15. We've got the 3 and we've got the 15 tracked. I have a 5 and a 25 here. So the number 5, if you're trying to get it from these numbers, it came from this 30 here, right? Because we had to split this thing in half and then we factored out the A value. 5 happens to be 30 divided by 2, because we cut this thing in half, times 3, because that's the A value, right? 2 times 3 is 6, 30 divided by 6 is 5. So in terms of these letters here, the number 5 happens to be this number in the center, which I'm going to label B for now, happens to be B divided by 2 times the A value. So I'm going to be able to replace this negative 5 with this. Now, if you notice, I have a 5 here and a negative 5 there, which means I have to park a negative out in front in order to make the signs match. So we found the 5 in these numbers, we found the 3 in these numbers, we found the 15. The only thing left is 25. Now, if you notice, 25 happens to be 5 squared, and that came from here as well. Take this number, cut it in half, and then square it and tack it at the back. So 25 happens to be this thing squared. Now I'm going to have to wedge that in here. B over 2A all squared. Gross. But everything is accounted for. Now I would like, well, ta-da, we're done. This expression here takes these 3 numbers, the thing attached to the x squared, the thing attached to the x, and the thing that has no x attached. And it will, if you plunk the numbers in there, it will spit out your answers. And it saved you all this nonsense about converting to vertex form, and will never, ever, ever, ever have to think about completing the square ever again. This is a bit of a mess, so I'm going to try and clean it up a little bit. First off, I have a fraction here that's squared, so I'm going to clean that up. X equals minus B over 2A too many markers, plus or minus have this a out front. Then I have b squared is b squared. 2a squared would be 4a squared minus c. All over a. Oops, a in pink. Okay, so I have an a multiplied by, divided by a squared. So this a is going to eliminate an a in the bottom. And nobody likes a fraction in a fraction. So to fix that, I'm going to take this fraction here, and I'm going to multiply the top and the bottom by 4a. Now, if I do that, 4a times 4a in the denominator, those are going to cancel each other out. So if I rewrite this whole line again, x equals minus b over 2a plus minus the square root. This b squared, colors are starting to be cumbersome, b squared over 4a multiplied by 4a minus c times 4a. I'm just going to write AC because that's how they go in the alphabet. And in the bottom of this radical, I have 4a times a, which is 4a squared. And you say, this doesn't look better yet. And you are right. This is going to divide that. And one of your exponent laws allows you to apply a radical separately to the numerator and the denominator of a fraction. So if I do that, I will end up with x equals minus b over 2a plus or minus square root. Well, this and this divided each other out, so all I'm left with is the b squared. Subtract 4, multiplied by the a value, multiplied by that c value, all over top of the square root of 4a squared. Your exponent law allows you to apply the radical separately. Now, if you look at this thing in the bottom, the square root of 4 is 2, and the square root of a squared would be a. So this thing in the bottom is actually 2a. And if you look at what we have here, that's a fraction and another fraction with a common denominator. They both have 2a in the denominator, so I can write this as a single fraction. Like so. And there you have it. I have the answer to this nonlinear expression written in terms of the coefficients on the x squared, on the x, and on the thing with no x at all. That was a lot of work. As I erase this, and you're saying, goodness, how am I ever going to remember how to do that? I have a surprise for you. You don't have to remember how to do that. This thing is, I don't know, let's say 1,000 years old. So you don't have to prove this ever again. This is an established fact. This has been used to build trebuchets and to launch people to the moon and all sorts of applications. So you don't have to prove it, you just have to use it. So to demonstrate how easy this is now that we've built it, I have an A value, a B value, and a C value. So the solution to this would be x equals the B value, that's here, but negative, plus or minus the B value squared, so that would be 30 squared, minus 4 times the A value, that's 3, multiplied by the C value, which is negative 15, all divided by 2 times the A value, which is 3. So there's your model, shove in the numbers. You start working it out, have negative 30 plus or minus. 30 squared is 900. 4 times 15 is 60, and 60 times 3 is 180. The negative times a negative is a positive, so I didn't need that much radical there. 2 times 3 is 6. Nine hundred and 180 is 1,080. I'm going to need a calculator to do the square root of 1,080, so let me do that. 1080 gives me 32.863 over 6. And now I have this little plus minus to deal with. That's going to generate 2 cases. Case 1, x is negative 30 plus 32.863 over 6. Or case 2, x is negative 30 subtract 32.863. So I'm going to do this one first. Negative 30 plus 32.863 would give me 2.863 over 6. And 2.863 divided by 6 is 0.477. Okay. Case 2. Negative 30 subtract 32.863 gives me negative 62.863. And 62.863 divided by 6. I think I lost a decimal there. 63 divided by 6 gives me 10.477. So, at the end of all that, because I built this ahead of time, I was able to use this number, and this number to work out the 2 solutions without having to use completing the square to convert this into a linear expression I could actually solve with my linear algebra. So all you need to be able to do is find your A, your B, and your C, dump them in the equation, off you go. I'm going to clear this off, make a new example, and we'll try it again. All right, I have another example here of a nonlinear equation. but I'm going to try and use this to solve. So notice I've got an A, a B, a C, and this thing is equal to 0. So if I just note, the thing attached to the x squared serves as A in this equation. The thing attached to the x serves as the B in this equation. And the number with no x attached to it serves as the C in this equation. And there better not be another number because I don't have any other numbers to fill into this formula. So I just have to fill 5, -15, and -2 into this hot mess. So -15 plus or minus the square root of -15 squared minus 4 times 5 times -2, all divided by 2 times 5. Okay, so off we go. -15, positive 15, plus or minus 15 squared is 225. 4 times 5 is 20. 20 times 2 is 40, and a negative times a negative is positive. 2 times 5 is 10. 225 and 40 is 265. I'm going to need my calculator to do this. Square root of 265 gives me 16.279. So I'm at the place where I have to deal with this plus or minus. So case 1, x is 15 plus 16.279 over 10, or case 2, x is 15 subtract 16.279 over 10. So this one here, 15 plus that would be 31.279, and that divided by 10 would be 3.128 if I round. This case, 15 minus 16.279 will be negative 1.279 divided by 10. X is negative 0.128 if I round 3 digits. There we go. Now, I think that took 2 minutes, which was much better than all the algebra work you had to do in order to complete the square to solve this. So this little tool is very handy. I'm going to clear this off. We're going to try one more thing. So again, A, B, C, just dump them into the equation. So I need -5 plus or minus square root of 5 squared minus 4 times 3 times 30, all divided by 2 times 3. Okay, so I have -5 plus or minus 5 squared is 25, 4 times 3 is 12, 12 times 30 would be 360, and a negative times a positive is a negative. 2 times 3 is 6. 25 subtract 360 would be negative 335. And we've reached a tiny problem. You cannot square root a negative number. This ends up generating an error. It's not possible. So in question 1, did I do something wrong? Did I mishandle a negative? So go check. This negative was there because of the formula, so it has to be there. This negative is part of the formula, so it has to be there. None of these numbers were negative, so there shouldn't be any other negatives wiggling around there. a negative times a positive is a negative, and this number is bigger than that, so I end up with something less than 0. So this quadratic formula even was able to stop you when the expression you were trying to do didn't have an answer. Now keep in mind, this thing is a parabola. And if you draw a parabola in the right way, this one that I just drew here doesn't cross the x-axis. So there is never a place where it's equal to 0. So if that's the case for your quadratic, the quadratic formula will tell you that it's not going to work. Which sort of brings us to a helpful little feature of this. It would be nice to know if this was going to work before I wrote all this crap down. So if you look at where the error occurred, that's this thing inside of the radical, which was this part, which over here in the formula is this much. This thing is called the discriminant. Now that word there, the only other word I can come up with that has that same root would be discriminate, which is to form an opinion on something before you actually get started. So we're going to look at a quadratic, and we're going to use this much to see if it's actually going to work before I get too carried away. So I'm going to clear this off and then write a new one down. So let's try 4x squared plus 6x minus 3 equals 0. Now, in a minute, I'm going to dump all these numbers into the quadratic formula and get a solution. But before I do all that work, why don't I just give it the sniff test here and see if it's going to have an error in it before I write all that stuff down. So look at your b value and square it. That's this part. 4 times your a value times your c value would give me 36. 4 times 4 is 16. 16 times 3 is 48. And a negative times a positive times a negative is a positive answer. That gives me 84. Now that's a positive number. That means the radical will have an answer. So I should feel free to continue. So x will be minus 6 plus or minus the square root of 84 over 2 times my a value. Now I'm not going to finish this because I think you've got that part. You can use your calculator to answer it. But by doing this b squared minus 4ac thing, by evaluating the discriminant first, I knew that this was going to have an answer, so I should be encouraged to continue. I'm going to erase this, try a different one. So I'm going to evaluate my discriminant on this, take my b value and square it, 36. And then I need 4 times the a value times the c value. 4 times 5 is 20. 20 times 10 is 200. And a negative times a positive is a negative number. So that gives me negative. Well, who cares? Smiley face, because it doesn't matter. The fact that this number is bigger than that means my answer is going to be a negative, which means my radical is not going to work, so I might as well stop here while I'm ahead. This thing won't have any solutions. The discriminant showed me that. So I do have one last example to do where there's a number here, and then I think we're good to go for the practice problem. So I still have an A and a B and a C, but this time there's a number over here. And there's no place in my quadratic formula for that number. So I'm just going to do some gathering of like terms. Right? I have a number here with no letters attached, and I have a number here with no letters attached. So pull it over. Subtract 20 from both sides. Gives me 2x squared plus 8x minus 16. So by doing that, I have successfully rendered this as something that just has an A, a B, and a C value. I'm going to check my discriminant to see if this has solutions. So B squared, 8 squared would be 64. My A value is 2. My C value is negative 16. 2 times 4 is 8, and 8 times 16 would be 80, and 48 is 128. And a negative times a positive times a negative is a positive. 128 and 64 would give me 192. So that's a positive answer, which means the radical is going to spit out something. It won't fail. So I should continue to get the rest of this solution. X is minus 8 plus or minus the square root of 192 over 2 times my A value. So X will be negative 8 plus or minus the square root of 192 over 4, whatever that is. So if you have a number over here, you got to get it over so that you only have an A, a B, and a C. Once you have an A, B, and a C, then check your discriminant to see if it's going to actually have solutions. If this spits out 0 or a positive, then continue with your quadratic formula, generate your two cases, and get your answers.